Lecture problem 1. A man walks 50 meters due west, then 50 meters at an angle of 60 degrees north of west. Determine the magnitude and direction of the resultant displacement using the vector component method. First, let's sketch a diagram representing this motion. The man is going to walk toward the west direction 50 meters. Let's represent this displacement with the vector A. After completing the first 50 meters, the man walks another 50 meters, but this time at an angle of 60 degrees north of west. Let's represent this displacement with the vector B. The resultant vector, and that's the vector that we're trying to solve for, is that one that is represented by the sum of vector A and vector B. Since vector A and vector B are mounted tip to tail, therefore the resultant vector is that one that starts at the tail of vector A and ends at the tip of vector B. The next thing that we need to do is to establish the system coordinate. I'm going to choose the east direction to be my positive x and my north direction to be the positive y. The resultant vector r is the sum of vector A plus the vector B. At this point in time, since the vector A and vector B are not lined up, we cannot add the 50 meters using this equation. This is not the way it works with vectors. In order to be able to find the magnitude of the resultant r, we need to break this equation into components. The rx is going to equal the ax plus the bx. The x components do add up because they are lined up. And in a similar way, the ry equals the ay plus the by. Notice in our example here that the ax is equal to negative 50 meters because it's pointing towards the negative x. However, the ay is equal to 0 because the a vector is lined up with the x-axis. Any vector that is lined up with the x-axis automatically has 0 y component. And the same thing can be said about vectors that are lined up with the y-axis. Those vectors do not have x components. Now, let's find the x and y components for vector b. To do that, we need to turn this vector b into two vectors. You start at the tail, you move parallel to the x-axis, then parallel to the y-axis to form those two components. When you break a vector into components, you always end up with the right triangle. Using that right triangle, we can figure out the two components. The bx clearly is pointing towards the negative x, therefore it's a negative component. Using the trigonometry of this right triangle, the bx is equal to the b vector times cosine the angle of 60 degrees, which is going to equal negative 50 cosine 60. In a similar way, the by component is positive in this case because it's pointing towards the positive y. Since the x component is b cosine, therefore the y component is going to be b sine 60, which is equal positive 50 sine 60. Now that we have evaluated the x and y components for vector A and vector B, we can easily evaluate the magnitude of vector r and its direction. Notice that the x component for the vector r is clearly the sum of the ax plus the bx, and the y component for the vector r is equal to the by component because the x component for the vector A is 0. Now we can solve for the x component of our resultant vector, which equals the ax plus the bx. The rx therefore is going to equal ax, which is negative 50, plus the bx, which is also negative 50 cosine 60. Solving for the x component of the resultant vector, we obtain negative 75 meters. In a similar way, we can solve for the y component of the r vector, which is ay plus by. Notice that the y component for the a vector is 0, therefore we have 0 right here, plus the y component, which is 50, it's a positive 50 sine 60 degrees. Solving for the y component of the vector r, we obtain positive 43 meters. Now that we have solved for both x and y component of the resultant vector, it's very simple to solve for the magnitude of the vector r using the Pythagorean theorem. R is going to equal the square root of rx squared plus ry squared. Solving for the magnitude of the r vector using the rx and the ry, we obtain 86 meters. To solve for the direction of that vector, we need to solve for the angle that is made with the x-axis. The angle theta can be obtained using the inverse tangent of ry, the y component, over rx, which is the x component. Solving for the angle theta, we obtain 30 degrees. This value of 30 degrees has very little meaning. In order to precisely find out the proper direction of the vector r, you can do it in two different ways. You can look at the diagram. Clearly, the angle theta that is made between the r vector and the x-axis is pointing north of west. This is one way how to do it. The other way to do it is by looking at the components of the vector r. The rx component clearly is a negative component. However, the y component is a positive component. In this case, the vector r must be in the second quadrant and therefore pointing in a direction that is known to be north of west.